Okay, if we look at the practice quiz that I gave you to prep for your test on Thursday, we're looking at question number 1. The graph of y equals 3x squared minus x cubed has a relative maximum at what? If you want to find out about the maximum and you're given the original function, you need to take the first derivative, which is going to be 6x minus 3x squared. Now, we're going to take this derivative and set it equal to 0, factoring out a GCF, and we're going to find the critical points. One critical point is going to be at x equals 0, the other one at x equals 2. I'm then going to do a sign diagram, placing my two critical points on the sign diagram. This is the sign diagram of the first derivative, not the original function. I'm going to choose test points, and I'm going to plug those test points into the first derivative to see if the answer would be positive or negative. Plugging in -1, I will get a negative. Plugging in a +1, I will get a positive. And then plugging in a 3, I will get a negative. So I'm looking for a relative maximum. A maximum occurs when you change from increasing to decreasing. So on the sign diagram, remember these plus and minuses mean where the original function, here f of x is decreasing, here it's increasing, and then decreasing. So the maximum is going to occur at 2. Now, if you want to find the ordered pair, that's when you take this where the max occurs and plug it into the original. So we have y equals 3 times 2 squared minus 2 cubed, and that will give me 4. So my maximum is at 2, 4 only. Okay, let's turn to question number 2. This one has a picture of the graph of the original function. This function is cubic. Okay, therefore the derivative, if we're looking for a picture of the derivative, it would be 1 power less. So 1 power less than cubic is squared. So it has to be a picture of a quadratic. So C is automatically eliminated. Now looking at these, I've got to determine where, which of these quadratics would it be. Now if this is the original function, the first derivative, where the first derivative is positive is where f of x is increasing. Okay, and then where the first derivative is negative, that's where f of x is decreasing. So let's look for where f of x is increasing. It's increasing from here to here, right there, and then from right here up. Those are the two places that it's increasing. And then it's decreasing, or the derivative is negative, where the original function is decreasing. So we got positive, this would be negative, this would be positive again. So those are the values of the derivative. That's what those signs mean. Where the tangent line is 0, where the tangent line is horizontal, that's where the derivative is going to be 0. So the derivative should cut through the x-axis here because that's where the max and mins are on the original function. So the slopes of that would be 0. So the derivative should cut on either side of the origin. So now I can eliminate b and I can eliminate e because they do not cut through on either side of the origin. So we're looking at these two now. Now keep in mind, up until that cross at the x-axis, what should the derivative be? It should all be positive there before that dot. So here's the dot, here would be the dot for this one. It is positive before. In between the two dots, it should be negative. That's true. And then after this last one, it should be positive again. So A is the one that matches. Let's look at number 3. Number 3 says, let g be a twice differentiable function. All right, so g, you can take the derivative of it twice. The first derivative is positive everywhere, which means g of x is increasing. And the second derivative is positive, which tells me that g of x is also concave up. And that's for all real numbers. So the whole function is increasing and concave up. So I've got two ordered pairs from the original function. What can be a value of g of 6? Well, since the original function, I know because the first derivative is positive, is increasing, so it's got to go from 12 to 18 to a higher number. Therefore, A and B cannot be the answer. They would not show that it's increasing. So let's keep going. From the homework problem we did the other day, 12 to 18 is 6. If I were to add another 6 to 18, I would get 24. We do not want that constant change. That constant change indicates that it's linear. Well, it can't be linear if it's concave up, because concave up looks like that. So now D is out. So now I'm trying to decide between 21 and 27. If I were to do a quick little sketch, 1, 2, 3, 4, 5, and let's say at G of 4 is 12, let's say 12's here, and G of 5 is 18. If I did G of 6 as 21, that would be barely a change. That's not looking very curved up. I need it to be more. So therefore, to get the concave up, it's got to be 27. Last one for this video is number 4. Determine which of the following statements are true about the original, the derivative, and the second derivative of f of x. Number 1, if the derivative equals 0 at c, and the second derivative at c is positive, okay, that tells me it is going to be concave up, then we would have a minimum. True. Think about what concave up looks like. You got to have a minimum around concave up. So this one is true. That's the second derivatives test from our notes. If the first derivative is positive, then the original graph is increasing. That's true. We've been doing that for several weeks. If f of x has a point of inflection, okay, then the first derivative has a relative max or min. Okay, so let's think about that. If it has a point of inflection in the original function, that's when the second derivative equals 0. Well, the second derivative equals 0 where the first derivative has a max or min, because if the graph of the first derivative has a max or a min, the slope right there would be 0. So this is also true. So our answer is E, 1, 2, and 3. I will be posting in a separate video the other remaining questions from this packet.